Hello all of you. Welcome to the 21st lecture on the course on analysis and modeling in chemical engineering. In this week, we will learn about evaporators and how do we model that. In the previous week, we discussed the modeling of chemical reactors, and now we will apply the modeling principles on the case of a evaporator. So, first we will discuss single effect evaporator, and then we will discuss multiple effect evaporators, both forward feed and reverse feed in this week. So, to begin with, what exactly is a evaporator? So, evaporator is kind of a separator where we want to separate a non-volatile solute from a solvent, right? And it is a complete separation. That means the solute is assumed not to go in the vapor phase typically, right? It's completely non-volatile. So, in that case, we can therefore achieve 100% separation of the solute from the solvent, and therefore, either we can get a pure solvent by condensing the vapor that is coming out, or we can get a thick concentrated liquid containing more solvent that can also be used for concentration therefore, right. And what really happens in the evaporator is very simple. So, we have a tank where a feed enters. The feed can be liquid or vapor or mixed, but we will consider mostly liquid feeds. So, feed comes in there, and we have some liquid there and some vapor forming here, because we raise the temperature of this feed to its boiling point, and we do that by heat exchange typically provided by steam that is condensing inside these heat exchange tubes shown here, right. So, steam is not in direct contact with the liquid inside the evaporator, it is only providing the heat exchange, and typically we start with like saturated steam that condenses inside, and we get a condensed steam at the end, and the feed inside here, it is raised to the boiling point, and therefore we form a vapor that is typically pure, that comes from the top, and from the bottom we get a concentrated liquid, right. In some sense, evaporation is similar to distillation. In distillation also we are making use of the differences in the boiling point, but distillation applies to multi-component system that has difference in their boiling points, right. So, in that case, we do not necessarily have a non-volatile solute. We have solutes or components of different volatility, different boiling points, and therefore, we can separate them by this distillation process, very similar to what we are doing here. But the main difference is that in the case of distillation, we do not typically achieve 100% separation, but in evaporation, we can get 100% or near 100% separation. So, going forward, if we think about an evaporator, there are certain measures of the performance of the evaporator. The first measure is like how much kg per hour of solvent is evaporated, that is what we know as the capacity. Then how much steam is consumed in order for that to happen, that is my steam consumption. And the ratio of the capacity to steam consumption, that is the kilograms of solvent evaporated per kilogram of steam fed, gives me what is known as a steam economy. So, clearly we want to have high capacity, we want to have low steam consumption, and therefore, we want to have high steam economy as a result of that. Going forward, if we look at what are the variables and model parameters which are important for evaporator. So, we are going to do mass balance, and we are going to also do energy balance. In the mass balance, we will do the mass balance overall and mass balance for solutes only, and the energy balance will be applied on the entire evaporator. So, we have certain variables here representing the mass flow rates. The feed mass flow rate is F. Unlike the case of chemical reactors where we work with molar flow rates of different species, we work with mass flow rates here. There is no chemical reaction going on here. It is simply evaporation process where the non-volatile solute comes from the liquid phase and the volatile solvent comes from top. So, we have some feed mass flow rate, and we have some steam mass flow rate that is used to provide the heat exchange. necessary to raise the temperature of the evaporator to its boiling point. And clearly, whatever steam comes in, the same mass of steam condenses and comes out of the heat exchange tubes. But the feed basically gets divided into two parts, a vapor part with a mass flow rate V and a liquid part which is having a mass flow rate L. Now clearly, as we did for the energy balance for chemical reactors as well, whenever a feed is coming, it is carrying some energy along with it, thermal energy, that we can characterize in terms of enthalpy per unit mass now. Again, we were using molar enthalpies earlier, but now we are talking about enthalpy per unit mass because it's single component solvent and only one solute. And this enthalpy corresponds to some temperature Tf of the feed. Now, the steam also carries some enthalpy Hs. As per notation, we will use capital H when I am referring to a vapor or gas phase, and I will use small h when I am referring to the enthalpy of a liquid phase. So, we have some enthalpy Hs of the steam at some temperature Ts, that is typically saturation conditions, and a corresponding pressure Ps. And once it condenses out, now we have a liquid condensate, therefore I use a small hs. At the same temperature, at the same pressure, it is only the latent heat that is coming from the heat exchange tubes. We don't assume any sensible heat change typically inside the heat exchange tubes. So the temperature and pressure of the steam will remain same as the condensate. Inside the evaporator, we have another pressure and temperature. Clearly, we want Ts to be higher than T in order for heat exchange to take place and for raising the temperature of the feed liquid to its boiling point. And that boiling point corresponds to the pressure, the operating pressure inside the evaporator P. Finally, we get a vapor that is having an enthalpy. Again, I use capital H because it's vapor phase, HV, enthalpy per unit mass, and at the same temperature as that in the evaporator. Just like in the CSTR, we have the exit conditions same as the conditions inside the reactor. Something similar we are doing here. I just want to bring in some similarities in our approach. In fact, it is a simpler system because there is no chemical reaction. And the liquid carries some enthalpy HL, small hl, and at the same temperature as the evaporator T. So, these are the variables that we have, and now we go ahead and write the mass balance equation. First, the overall mass balance that gives me that the feed F that can either go into the vapor or the liquid. So, basically we can write F is equal to L plus V. I again remind you that the steam is not mixing with the liquid inside the evaporator, it is only providing heat exchange. It is passing through some kind of tubing and condensing it inside, right. So, for steam, whatever flow rate comes in, the same flow rate goes out. We write the mass balance only for the liquid in the evaporator, that is F equal to L plus V. And then we can also write a solute mass balance considering only one solute. So, let us say there is some overall mass fraction ZF of solute in the feed, then F into ZF becomes the solute mass in the feed, and that is typically going in the liquid phase. So, we have L into XL, where XL is the mass fraction in the liquid phase, right. We assume here that in the vapor phase there is no solute. In general, we can have an equation FZF is equal to LXL plus VYV, where YV is the mole fraction of the solute in the vapor phase. But if I assume that the solute is completely non-volatile, then we are going to drop this term, set it equal to 0, and then we have the simple equation, right. So, I use Z here just to indicate that it can be liquid or vapor or a mixture of both. It is kind of an overall mass fraction. But if I am working with liquid feed, which I will typically do, I can replace that with XF, that is the mole fraction in the liquid feed that is coming in. Going forward, we can write the energy balance equation as well, again very similar to whatever we had there in the case of a reactor, except there is no chemical reaction happening here. So, the input that is coming in is the energy of the feed, that is F into HF. HF is the enthalpy per unit mass and F is the mass flow rate, mass per unit time. So, FHF becomes the enthalpy per unit time that is coming in from the feed, and similarly SHS becomes the enthalpy per unit mass that is coming from the steam that is coming in, right. I have said earlier that the steam is not mixing with the liquid inside, but the steam can still do energy exchange. That is why we are using it, and therefore, in the energy balance equation, we are considering both as opposed to the mole mass balance equation, where I did not consider a steam here. In principle, I could have written F plus S is equal to L plus V plus S. S will anyway cancel out, but we again note that steam is not mixing with the liquid in the evaporator. So, this is my input, and the output we have three stream: a liquid stream that carries enthalpy per unit mass of HL that comes here, a vapor stream that carries the enthalpy per unit mass of HV that comes here, and finally a steam condensate that carries an enthalpy of HS, enthalpy per unit mass HS, right. In order to simplify this, I am going to subtract this quantity from both sides. This will be some kind of a reference, and we will see like how it is useful. And if I do that, then we get an equation of this form. So, rather than talking about absolute value of enthalpy, now we are talking about enthalpy differences. So, this is the enthalpy difference between the feed and the liquid concentrate, the enthalpy per unit mass difference. Similarly, this is the difference between enthalpy of the steam and the steam condensate, and this is the enthalpy of the vapor, again with reference to the liquid enthalpy that is coming out. So, now we will make some more assumptions. That is not always true, but that will help us simplify the math here. So, we are going to assume that the steam that comes in is saturated, and therefore, there is no change because of the sensible heat change for the steam. The only heat that is given off by steam through this heat exchange tube is the latent heat, because steam is condensing inside, and therefore, we have used the same temperature for the steam coming in and the condensate temperature and pressure. So, we are going to assume that to be saturated. We are also going to assume, and this is a more serious assumption, that the vapor is also saturated, right. What this means essentially is that in reality the solute is going to raise the boiling point of the liquid, right. So, in true sense, if you had, let us say, a pure water in contact with its vapor, then the vapor pressure of the thing that we get in the liquid should be same as the pressure in the gas phase, right. But if I have an impure solvent, impure water or water containing a solute, in that case the solute will invariably increase the boiling point. That is an effect that you may have learnt earlier, right. So, we ignore that increase in the boiling point. So, there are ways to include that, but for simplicity we are going to assume that there is no elevation in the boiling point, and as a result we can again assume that the vapor is also saturated. Again, vapor can also be superheated. In that case, we have to also worry about the sensible heat change in the vapor that is coming because of the heat capacity of the vapor here, but we are ignoring that. We are assuming that the vapor comes out and it is saturated. And then finally, as I have said earlier, we assume liquid feed, and Cp, the heat capacity of the liquid, can in principle depend on temperature, and in fact it does depend on temperature, but we are going to assume for simplicity that it is constant, or we can assume that the dependence on temperature is very weak, right. So, if I do that, then the difference in the enthalpy of the feed and the liquid is purely because of the sensible heat change, and that can now be written as the heat capacity into temperature difference for the liquid, that is Tf minus T, and this enthalpy change of the steam when it goes from steam to condensate, again I can express in terms of the latent heat of the steam in the given condition of temperature and pressure, that is Ts and Ps of the steam, and assuming that there is no boiling point elevation and there is no sensible heat for the vapor, we can also write that the difference of the enthalpy per unit mass of vapor with that of the liquid concentrate can be given as the latent heat, again for pure solvent, at temperature Tp, right. So, this is, I would say, a more serious assumption. For steam, we can always ensure that the condition is saturated because it is a pure liquid, but for the concentrate that is forming, clearly there is going to be a concentration dependence of the boiling point, and therefore, the latent heat can be a function of composition in general, but for simplicity here I am assuming that latent heat is same as that for the pure solvent, right. And these values for water can be taken from steam tables. They are already tabulated there. So, for a given temperature and pressure condition, we can get the latent heat, and in fact, the pressure condition is defined by the temperature condition or vice versa, as we have discussed in the pure water phase diagram earlier. So, once I know that this is the temperature at which steam is boiling, then that corresponds to a particular value of pressure. So, temperature and pressure are not independent variables. At saturated conditions, the pressure is defined by the temperature or vice versa. Similarly, since we have assumed that the boiling point elevation is neglected, so therefore, the temperature is defined by the pressure or vice versa. So, if I make the assumptions, I can basically replace these enthalpy differences in the first equation by whatever we have got here, and then I have a rather simple equation that gives me the energy balance for the evaporator, right. Keep in mind that it may appear to be very simple and linear equation, but this latent heat does depend on the temperature of the steam, and this latent heat does depend on the temperature of the liquid inside the evaporator, and this can be a very much nonlinear function if you indeed try to plot the values from the steam table, right, and that dependence must be taken care of when we write this equation, right. So, these are not really constants, they do depend on temperature, and we cannot ignore their temperature dependence because latent heat does vary quite a bit with temperature. Okay. So, going forward, we can also write heat transfer equation that corresponds to the heat transfer from these heat exchange tubes to the liquid phase, and this q dot, assuming that there are not much losses taking place, is something like the steam flow rate into the latent heat of steam. This is the energy that we get, the latent heat that we get by condensing steam, and that is basically my UA delta T. That is how we define heat transfer in heat exchange tubes, where U is my overall heat transfer coefficient for the heat exchanger and A is my effective heat transfer area. Although I said that I am not considering losses, but if there are losses, there are ways to include that by appropriately changing this effective area. It may not be the true area that we have in the heat exchange tubes, it can be a lesser area, or we also have a mechanism to basically choose this heat transfer coefficient that also accounts for the losses and things like that, right. So, this is a more general heat transfer equation that may also account for losses provided that we have experimental data to support it. So, this delta T, that is the temperature difference between this steam tube and the temperature of the liquid outside, is given as Ts minus T, and now we have basically the entire set of equations that we need for the single effect evaporator. What are those equations? So, we have again an overall mass balance, a solute mass balance, an energy balance, and finally a heat exchange equation, right. In addition to that, as I have said, I am going to get the latent heat from the steam table. So, in general, we can imagine that latent heat of the steam can be a function of the temperature and pressure of the steam, and latent heat of the liquid can be a function of the temperature and pressure of the liquid. And I have already said, since we assume that we have saturated steam, so my pressure of the steam is defined by its temperature, again that can be borrowed from the steam table. And since the liquid inside is also considered saturated for the purpose of the calculations, we can also have a relation between the pressure and temperature of the liquid, right. So, with that we have in total like 8 equations in this case. These ones, although I am listing it now, we will not typically list in future. We just take it for granted that the latent heats and the pressures may be obtained from the temperature and other conditions from these property relations, right. So, these are not typically listed, but keep in mind that this must have be used here, and these are the equations which are basically making the first 4 equations non-linear and difficult to solve. So, let us look at the variables. What are the variables we have? So, we have 4 mass flow rate of the feed, the steam, the liquid and vapor. We have 2 solute mass fractions, the XF and XL, XF for the feed, XL for the liquid, that is concentrate, that is going out. And then we have 3 temperatures, temperature of the feed, temperature of the steam and the temperature of the liquid in the evaporator, which is same as the temperature of the vapor that is coming out and the temperature of the liquid that is coming out. And we have fluid properties lambda S, lambda and Cp that will come from the property relations. And finally, we have 2 pressure values, the pressure of the steam and the pressure of the liquid inside the evaporator. And because of this heat exchange tubes, we have additional properties for the heat exchanger, which is the overall heat transfer coefficient and the heat transfer area, right. And these are 2 of them and these are 3 of them, sorry. So, in total we have 4 plus 2 plus 3 plus 3 plus 2 plus 2, right. So, we have total 16 variables in the problem and we have 8 equations, right. So, we can find the degree of freedom and we have to specify 8 of those variables as given, only then we can solve it, right. So, whenever we first look at any problem concerning like any chemical engineering application in general, but evaporator in this case, the very first thing we should do is to ensure that do I have enough variables and enough equations to solve this problem, and of course, the equations has to be independent. So, clearly the equations you can see here, these equations appears to be independent. I will not do a check on that, but these are appearing to be independent. If for example, I had written mass balance also on the solvent, that would not have been an independent equation, because that would have been something like F into 1 minus XF. This is the amount of liquid solvent in the feed and that is equal to L into 1 minus XL, that is amount of liquid solvent in the liquid going out, right. And this equation, if I would have written, will not be an independent equation, because this can be done, this can be obtained by basically subtracting 1 minus 2. So, this is a wrong equation. If I would have included that, I would have got an additional equation, but that equation may not have been independent, right. So, these checks we must do before setting up any problem, particularly on in the material and balance, energy balance context. So, going forward, let us look at how we can possibly solve it, right. So, we have to clearly take 8 of the variables as given. Let us say I make this particular choice. Later on we will discuss that these choices are very important, because they are going to dictate how easy or difficult it is to solve the equations which are given to you, right. In many cases you don't have a choice, because a plant is running and you don't know all the variables, you know some variables. But when you are doing like a design of a plant, then you can take these as the given variables, which are kind of you want to keep it fixed, and the other ones becomes more like a design variable which you can find from solving the equation, right. So, we have now 8 unknowns remaining in the problem, and clearly I can use the last 4 equations here to get the latent heat and the pressures, and henceforth I will not be discussing therefore these equations at all, and I will simply say that these are known, but keep in mind that these are coming from these property relations or steam table, whatever, right. So, once I get these 4, then V is an unknown for us, but V we can get from this equation, because I know F and I know L. So, V becomes equal to F minus L from equation 1. And once I know L and V, then I can now go to this equation. I also know my XF, so I can compute my XL as well. In fact, in this case, FL and XF, all of them are given, so we can do it even earlier. And now, once we know all of this, then we can go to the third equation, and I know the TF, I know T, and once I know TF and T, I can basically get this equation. I also know TS, and since I know TS, I can evaluate lambda S, which is a function of TS, and I can evaluate lambda, which is a function of T, because I know T, right? So the only unknown in the third equation is now my S, which I can get from equation 3 now. And finally, I can go to the fourth equation. Now I know S early, just now I computed it, and lambda S is a function of TS. I know TS, and U is also known to us. TS is known to us, T is known to us, so we can find A from the last equation, right? So this is a typical way we will go for like solving this kind of problems, but keep in mind that the actual solution scheme will depend on what is given to you and what do you have to figure out. In this case, we can pretty much do it sequentially without doing any simultaneous solution, but in the examples I will do later, you will see that I have to go for like some simultaneous solutions also in some cases. Going forward, let us see how we can look at how we can find the measures of performance I have defined earlier. So the capacity we had defined as the kg per hour of solvent evaporated, that is pretty much the V in our schematic, and that V we already have found from the material balance equation, the mass balance equation, F minus L. The steam consumption, that is the kg of steam fed per hour, that is my S, which again I can get from whatever I have done earlier, right? Or I could have got from the last equation if I knew the A. So I can also get it this kind of an equation if A was given to me. And finally, the steam economy, which is the kilograms of solvent evaporated per kilogram of steam fed, is the ratio of these two quantities, which is simply V by S in our case. So going forward, in the math so far, we have considered that there is no boiling point elevation, which is actually a serious assumption, because we know that the boiling point does elevate whenever we add a solute in this case, right? How can we account for that? So there are relations available in literature, of course from experimental data, that basically suggest how the boiling point of a solution depends on the concentration of solute or the weight fraction of solute as related to the boiling point of pure water. So these lines that you see here, they are called Duhring lines. These Duhring lines pretty much dictate how the boiling point of solution at given condition is changing with the amount of solute. So these different lines correspond to different weight fraction of the solute. This particular plot is for NaOH in water. And let us say I am talking about a weight fraction of NaOH equal to 0.4, then I am talking about this line here, and let us say we know that the boiling point of water in the given condition is something like this. We basically can look up the corresponding boiling point of the solution there, right? And as you know that the boiling point of water and any solution in general depends on the pressure. So therefore, we have lines corresponding to different pressures. So for example, if I am at this particular pressure, it is given in the units of pound per inch square, then I have the boiling point of water given as something like here. So I have the corresponding value of the boiling point of solution, right? And as you can see, the boiling point of solution is always higher than the boiling point of pure water in the same conditions. So this I have taken from this particular book. You can read more about it, but this data is available in literature. There's one other thing that I have also ignored and we didn't discuss so much until so far, is the heat of solution. Whenever we prepare a solution, whenever we mix a solute with a solvent, there is a heat requirement or heat released. If the solute likes solvent, then basically mixing is a spontaneous process. It will release heat. On the other hand, if solute does not like solvent, then mixing will require heat, right? So whatever heat is required or released because of the mixing process is referred as the heat of solution. Similar to heat of reaction, what we have discussed earlier, in this case, no chemical reaction is taking place, but we are basically forming a solution. In order to dissolve solute in the solvent, this is the amount of heat required or released is given by the heat of solution, which we have not considered so far. We only considered sensible heat changes, not the heat of solution. In order to also account for this and the boiling point elevation, we can also use something known as enthalpy concentration charts, which are also available for a variety of systems. And I am again giving you an example of NaOH solution. If I know my weight fraction, and if I know the corresponding temperature, then I can figure out what is the enthalpy relative to some reference, right? So this will be an alternative to whatever approach I have discussed. I can go back to my original equation where I worked in terms of enthalpies, and rather than making an approximation regarding the enthalpies in terms of the heat capacity, I can directly borrow the enthalpy values from the enthalpy concentration charts if it is available, and then we can directly solve the equation. That will be more appropriate way of doing it. But in case we don't have this data, in that case we can only assume that we have certain heat capacity and only sensible heat change is being considered and so on. Okay. So with that, I want to conclude the discussion on single effect evaporator. In the next lecture, I will discuss how we can use multiple effects in the evaporator, where we basically will have multiple evaporators in series, and then we will see like how we can perform mass and energy balance for those kind of systems. So with that, I conclude here. Thank you so much.